Assalamu alaikum. It's Ahlam Deep, and I'll be explaining Chapter 3, Kinetic Factors, Part 1. Before we start, please prepare your stuff. In our video for today, we are going to present the kinetic factors that affect the rate of a chemical reaction. We have seen in Chapter 2 that during a chemical reaction, the concentration of the product increases with time and a kinetic curve having this shape is obtained. For any reaction at t equals 0, the slope of the tangent to the curve has the highest value. And since the slope of the tangent to the curve is equal to instantaneous rate, so at t equals 0, rate is maximum. With time, the slope of the tangent to the curve decreases progressively. So, with time, rate decreases. After a long period of time, at t infinity, the tangent to the curve becomes horizontal, indicating a rate equal to 0, and this is the end of the reaction. But what causes the decrease in the rate of reaction? The collision theory explains this fact. The collision theory says that chemical reaction can only take place when the reacting particles collide with each other. These collisions must have sufficient energy, and the rate of a chemical reaction is determined by the frequency of successful collisions. Frequency means the number of collisions per second. Going back to our graph, we can explain its shape by using collision theory. Reactions are rapid initially because we have a large number of reactant particles. This means that we have a large number of collisions per second. With time, reactions slow down because the number of reactant particles is running out, and so we have a smaller number of collisions per second. Finally, the reactions stop because all of the reactant particles run out. This means that the number of collisions per second is 0. We have two containers. Each is holding particles that can react with each other. Both of the containers have the same volume. Remember that the rate of reaction depends on the number of successful collisions per second. In container 2, we have twice the number of particles in the same volume. In other words, the concentration of particles is twice that of container 1. This means that the number of collisions per second in container 2 will be twice that in container 1. And the rate in container 2 will be twice that in container 1. So, the concentration of reactants is a kinetic factor. The rate of reaction increases when the concentration of reactants increases, and vice versa. Vice versa means that when the concentration of reactants decreases, the rate of reaction decreases also. Therefore, we say that the concentration of reactants and the rate of reaction are proportional. When one increases, the other increases as well. Now, let's watch together a simple experiment which proves that when the concentration of reactants increases, the rate of reaction increases. Consider the oxidation reaction of iodide ions I- in acidic medium. To study the influence of the initial concentration of a reactant, consider 3 reactional mixtures A, B, and C, where we have the same reactants but different initial concentrations. The table here shows the initial concentrations of the reactants. In the mixtures A, B, and C, we have the same initial concentration of H plus and of H2O2. The initial concentration of I minus in mixture A is smaller than that in mixture B, smaller than that in mixture C. The variation of the concentration of the product I2 with time gives three kinetic curves. We notice that the rate of reaction at T equals 0 and at each instant of the reaction is bigger in the reaction system where the concentration of I minus is the highest. I'm talking about mixture C. Then comes mixture B, then A. Pay attention that the maximum concentration of the product I2 is the same for the three mixtures. Why? Since the maximum concentration of I2 depends on the limiting reactant H2O2, which is the same in the three mixtures. But the maximum concentration of I2 is reached in C before B, before A, where the concentration of I minus is the smallest. Also, for the same instant T, we notice that the concentration of I2 in mixture A is smaller than that in mixture B, smaller than that in mixture C. This can be noticed also by the color of I2 that becomes darker when its concentration is the highest. For the same reaction, if I minus was the limiting reactant and not H2O2, the shape of the curve will change. How? We obtain three curves in which the final concentration of I2 in C is bigger than the maximum concentration in mixture B, bigger than that in A, since the final concentration of I2 depends on the limiting reactant, which is in mixture C, bigger than that in mixture B, bigger than that in mixture A. Are there other factors that affect the rate of reaction? Yes, there are. First, we have temperature. When we increase the temperature of a reaction, particles will have more energy. This means they move faster and are more likely to collide with other particles, so the rate of reaction increases. Let's watch this simple experiment that you can perform at home with a vitamin C tablet. This experiment proves that when temperature increases, rate of reaction increases.
How does temperature affect the rate of a reaction? Let's find out using an experiment that you can try at home. We will be using the reaction of effervescent vitamin C tablets and water. To investigate the effect of temperature on the rate of reaction, we will be using 2 tablets and 2 glasses of water. One glass contains hot water and the other glass contains cold water. What do you expect to see when we drop the tablets into the 2 glasses of water at different temperatures? What do you observe? In both glasses, we see that the color of the solution changed from colorless to orange and there was effervescence. We also observed that the rate of reaction is different. In the glass containing hot water, the color of the solution changed more quickly and the effervescence stopped more quickly. In conclusion, an increase in temperature increases the rate of a reaction.
Let's go back to the oxidation reaction of iodide ions in acidic medium. To study the effect of the temperature on the rate of reaction, consider 2 mixtures A and B. These 2 mixtures have same reactants and same initial concentrations. They only differ by their temperatures. Remember that if I want to study the effect of one factor, I have to keep others constant. The temperature in mixture A is 20 degrees, while in mixture B is 60 degrees. This table summarizes the conditions of the experiment. So, the two mixtures have the same initial concentrations of the reactants. They only differ by their temperature. The variation of the concentration of the product I2 formed with time will give two curves. The above curve is that of mixture B, where the temperature is higher. But for both curves, the maximum concentration of I2 is the same, but it is reached in mixture B before mixture A, because the temperature in B is higher. So when temperature increases, the rate of reaction increases, and at the same time t here, we have the concentration of I2 in mixture B is bigger than the concentration of I2 in mixture A. Here, the production of I2 is more than that in beaker A at the same instant. Another factor affects the rate of reaction. It is the surface area of a solid reactant. We have here green particles of a solid reactant. These particles are reacting with other particles in solution. The particles in solution, the red ones, can only react with particles on the surface of the solid. Now we have the same mass of the solid reactant, but now it is in two blocks rather than one. With two blocks, we have a greater surface area than with one block. So here, the surface area increases. Now, all of these particles can react. So, the surface area of a reactant is a kinetic factor. When the surface area of a solid reactant increases, rate of reaction increases, and vice versa. Let's watch this simple experiment that you can perform at home with vitamin C tablet. This experiment proves that when the surface area of a solid reactant increases, rate of reaction increases.
How does size affect the speed of a reaction? Let's find out using an experiment that you can try at home. We will be using effervescent vitamin C tablets and water. To investigate the effect of particle size on the rate of a reaction, we will be using 2 glasses of water and 2 vitamin C tablets. One is a whole tablet and the other has been crushed to a powder. What do you expect to see when the tablet or the powder is added to the water? What do you observe? In both glasses, we see effervescence and the color of the solution changed from colorless to orange. We also observed that the rate of these reactions was different. In the glass to which the powder was added, the color change happened more quickly and the effervescence also stopped more quickly. In conclusion, a decrease in particle size or an increase in surface area results in an increase in the speed of a reaction.
Stirring also increases the rate of reaction by increasing the number of collisions between the reactant particles. Stirring can be done using a glass rod or using a magnetic stirrer and its bar. The last kinetic factor in our lesson, this is the use of a catalyst. What is a catalyst? A catalyst is a substance that accelerates a chemical reaction and remains unchanged from a chemical point of view at the end of the reaction. Therefore, in the equation of a chemical reaction, the catalyst is neither written on the reactant side nor on the product side. It is written on the arrow of the chemical equation. Before giving an example on the work of a catalyst, I'm going to ask you, have you ever heard by hydrogen peroxide? Hydrogen peroxide is a solution that you can buy from pharmacies. Hydrogen peroxide has many uses in our daily life. It is used to clean cuts and wounds. Dentists use hydrogen peroxide for whitening the teeth. Also, it can be used to sanitize fruits and vegetables. The chemical formula of hydrogen peroxide is H2O2. Hydrogen peroxide decomposes according to the following equation. It produces water, H2O, plus oxygen gas. But this reaction is very slow, so that if I pour hydrogen peroxide in this Erlenmeyer flask and observe it for many hours, I cannot observe the release of O2 gas. This slow reaction can be accelerated by using a catalyst. This is hydrogen peroxide, to which I will add a catalyst. The catalyst used here is manganese dioxide, MnO2. Observe here a very small amount of MnO2 is needed to catalyze the decomposition of this important volume of hydrogen peroxide. Once MnO2 is added, I can observe the release of O2 gas. Causing or accelerating a chemical reaction by using a catalyst is called in chemistry catalysis. A catalysis can be homogeneous or heterogeneous. In a homogeneous catalysis, the reactant and the catalyst form one phase. The reactant here is hydrogen peroxide, it is a liquid, and the catalyst here is Fe3 plus ions, which is dissolved in this solution. So H2O2 and this solution form one phase, and the catalysis here is a homogeneous catalysis. While in a heterogeneous catalysis, the reactant and the catalyst form more than one phase. This is the example of H2O2 with MnO2. MnO2 is a powdered solid, so it makes with H2O2 two phases, and this catalysis is said to be heterogeneous. A catalyst has many characteristics. First, a catalyst does not give more product. It gives us the same amount of product, but in a shorter time. Second, a catalyst is not a miracle. It cannot make impossible reactions possible. Also, a catalyst is chemically unchanged at the end of the reaction. A catalyst is characterized by its activity. We say that a catalyst is active if a very small amount of it can cause an important change in the rate of reaction. Also, catalysts are selective. This means that if I start from the same reactants, I can get different products by using different catalysts. Here, the reactant in the two reactions is the same. It is ethanol. If I use as catalyst Al2O3, I will obtain as a product an alkene. While if I use Cu as a catalyst for the same reactant, which is ethanol, I will obtain an aldehyde. To sum up, in order to increase the rate of a reaction, we can increase the initial concentration of reactants, increase the temperature of the reaction system, increase the surface area of the solid reactant, or simply use a catalyst. This is the summary of our video for today. Please write it on your chemistry copybook, and this is your agenda. See you soon in the next video. Wassalamu alaikum.